For Hamming codes, error detection and correction has this relationship or formula. That is, if the minimum Hamming distance is given, then it could detect d minus 1 errors. So you should have at least a minimum of 2 Hamming distance to detect 1 errors. That's what I have shown in the previous video, that parrot bit serves this one. That's for detection only, but to correct you have this formula. So first, this notation is a floor notation. Floor means after making a division, just take the whole part only. Discard any fraction part. So if a division result is 2.99, even if it's 99, just discard, take a whole part only. That's called the floor notation. So have this division and then take a floor notation, and that many bits you can correct. So if minimum Hamming distance is 2, 2 minus 1 is 1, 1 over 2 is a half, so you cannot correct any, just detect error. But if Hamming distance is 3, minimum Hamming distance is 3, then 3 minus 1 is 2, 2 over 2 is 1. So you can correct 1 bit error. So that's a relationship out of Hamming codes. So thus Hamming distance of 2k plus 1 is required to correct k errors. So if you plug in 2k plus 1 here, this becomes 2k plus 1 minus 1. So numerator is 2k, and then denominator is 2. So you can correct 2 errors. So you need to have a certain number of bits to make sure the minimum Hamming distance is guaranteed to either detect or correct. Some more details. So why do we need such many bits and so on? So let's qualitatively and then derive the relationship. Suppose we have a set of n bit code words consisting of m data bits, and then r is a redundant parities. So n is m plus r. So the whole number of bits is n, but only m bits are data information, but r bits are added as redundant. So what is the relationship we have in m and an r to detect or to correct error? Suppose we wish to detect and then correct one single bit error only, just one single bit error we want to correct. Then we find that an error could occur in any of n bits. Suppose let's have n as a 4, so you have a 1, 2, 3, 4 bits. Then if any of those changes from 0 to 1 or 1 to 0, then it should be invalid one. So what you find is that for one single information, since any bit could be in error, so if it's changed, it should be invalid. So by changing one of those n bits, then all of those n invalid code word should be guaranteed. So otherwise we cannot detect error at all. So in total, in any information, you need the n invalid code plus the valid one. So in any code, in any information, n plus one pattern is required. So let's analyze some more based on that. So we have n bits. So out of n, we are going to use m bits as data. Then the relationship is as follows. For each valid code, there should be n invalid code. So of total, n plus 1 patterns are needed to represent the number of valid code. So 2 to the m valid code, we need n plus 1 pattern. So why do we multiply n plus 1 is here? In previous slide, we know that there should be n invalid code and 1 valid. So if you want to have 2 to the m patterns as information, we need n plus 1 times 2 to the m. And that is smaller than 2 to the n. So we are using of total n bits. So what we should be able to represent is this many patterns. Then since we have n bits, this inequality should be satisfied. Since n is m plus r, so if we replace n by m plus r, then we have this one. Then we can take those out. Then this is the final inequality relationships. So for m bits, and then to have a certain number of redundant bits, so this relationship is needed to correct. So whole thing what you are doing is a one single bit error correction. One single bit error correction is the goal, and this relationship should be satisfied. So let's take a look at that relationship a little bit more. Suppose we have m is a 4-bit data. So data information is a 4-bit only. Then to detect 1 bit, to correct 1 bit error, how many redundant bits we should add? Since m is a 4, the redundant bits we should add, the minimally satisfying in this one should be 3. If we have r is a 1, then is 5, 6, 231 is 2. It's not true. So if r is 2, then you have 6 and 7, but right hand side is 2 to 2 is 4, not satisfying. But r is 3, you have 7 and 8, 2 to the 3 is 8. So this is satisfied. So we need to add 3 more bits for 4 bits data to correct 1 bit. So for single bit error corrections, 4-bit data, we need to add 3 more redundant bits, parent bits. That's what this relationship shows.